We would like to now build up on our experimental observation combined with the simple modeling approach, the Paris equation, and proceed further into the discussion of the crack growth rate. So it turns out that experiments reveal a line that is similar to this green line, whereas the Paris equation predicts a line that is flat in the log delta k versus dAdn space or plot. So now, therefore, we have split the regime into three parts: the low, the intermediate, and the high regime. So what is special about the high regime? Notice that here we're going towards fracture. When does fracture occur? It occurs when the stress intensity factor is equal to the fracture toughness of the material, right? Now, the stress intensity range cycles from the minimum value to the maximum value. The critical stress intensity value is the maximum value. So here, ultimately what is happening is that Kmax is going towards the fracture toughness. Remember, we're not writing the mode. If you like, this is mode 1. So this is the critical stress intensity factor or the fracture toughness. So the crack for this given value of the load, S max, corresponds to a stress intensity factor K max, which rapidly approaches now the fracture toughness at which fracture will occur. So the ultimate phenomena is governed by fracture mechanics. Up to that point, we're trying to model the growth of the crack. Now, in this case, remember that we assumed a certain value of R, the stress range, the stress ratio. The stress range itself is in some sense within delta K. So the question is, well, the following. How does the value of R influence the red line that we are predicting? Remember that the slope of the line is the exponent m in the Paris equation, and where it eventually lies, a little bit above or below, is also dependent on the factor c within the Paris equation. And the crack is growing because the load changes between S min and S max. So I have two parameters that control the nature of the load profile, and we have replaced those two parameters by the stress range, delta S, which goes into delta K, and R, the stress ratio. Now, the stress range is already within delta K, and therefore I am trying to now additionally incorporate the influence of R. And moreover, I'm going to try to do that within the intermediate range. It's also certainly a concern in the high range, but in the high range, I have a more important concern. An immediate concern is, well, how do I take into account this rapid increase of the green line versus my prediction, which is flat? Okay, so I'm going to try to do both of these. Let's start first with the effect of R. So we have the load profile, S min to S max. So it is a profile that has two parameters, either S min S max or delta S and R. This I have already taken care of because it is in the stress intensity range. The effect of R is what we want to incorporate. Okay, so now let's first try to think about what R does to our load profile. So I am going to draw a number of load profiles which have the same stress range, but they will differ by the value of R. So here, time is actual time, could have been number of cycles, and here let us start with a value of R that is -1. So S min is equal to minus S max. So that is R equals -1. Okay, So if I wanted to draw r equals 0, I would go like this. And I'm going to do that by preserving the range, delta s. So I'm going to try to draw the same amplitude. Okay. So the only thing that has happened is that r has increased in value. The corresponding stress profile has shifted up, but delta S is fixed, or at least I'm trying to draw it that way. The range of S is fixed in both cases. So apparently when R increases in value, this curve will shift up. So for instance, if it were 0.7, let's say, it would be a curve that looks like this, for instance. Okay. Now, as it keeps increasing, however, notice that the largest value it could possibly be is 1. Okay. So the largest value of R is 1 because it's the ratio of S min to S max. And if I write it explicitly, it is equal to S min over S max, which is equal to, if you like, S min over S min plus delta S. So for a given delta S, as S min increases, in other words, when this curve shifts out, eventually, the value of delta S will be irrelevant in the ratio and R will go to 1. Okay, so limit delta limit S min goes to infinity of R is equal to 1. Okay, so that's the largest value of R that I'll be concerned with. It's important because eventually we will see a parameter that looks like 1 minus R at some point in our models. Okay, so that's the prediction, that's the way the profile changes. So now I would like to ask you the following question. What I'd like to do is I would like to reflect the influence of R on that plot. So I'm going to draw this plot once again underneath. So it's on a log-log scale, dA dN versus delta K. Okay. And let's say this is the original plot for R equals a certain value. Okay. Let's say R is equal to, say, 0. Now my question is, what happens to this line? Okay, right? It is the line that corresponds to this law. In other words, for any given delta K, the point on the line is predicting the rate at which the crack grows. If for a given delta K, the line were higher, then the crack growth rate would be estimated to be higher. If it were lower, it would be estimated to be lower, etc. So now, this is the prediction of our model for R equals 0. That comes from, if you like, experimental data, okay, within or up to the high range. Now, when I change the load profile, keeping delta S fixed, right? So delta S, there is a certain crack size, there is a certain delta S, so the value of delta K is fixed. If I change R, if this has an influence on the physics, then the rate at which the crack grows will change. It will either go up or down, okay? And my question is, if R increases from 0, will this curve, this line, shift up or down? So if at that point it predicts a higher rate, it will be a line that lies over here, and it will predict a higher rate at every stress intensity range. So when R changes, say it increases, if at every point the rate of growth increases, then it's corresponding to this line, which means that when I increase R, the line will shift up. Okay? So my question is, however, is that indeed what happens? What is your expectation? When R increases, should the prediction of the model deliver a curve that is higher than the curve for R equals 0, so higher rates or lower rates? Conversely, if R increases, if R decreases, should this line lie below the red line or above it? Should I be predicting higher or lower rates for a given delta K? And think about that question for a minute. Now, if you've thought about it, let me give you a hint that might clarify your answer. What happens when R increases? What happens is, for instance, if we start with R equals -1, what we observe here is that this portion of the curve is spent under tensile loading, but here under compression, tension, compression. When we go to R equals 0, all of the cycle is spent under tension. So let me ask you the question, which do you think is more critical with respect to fracture and ultimate crack growth? Okay, vice versa. Crack growth and ultimate fracture. Now, because this profile is spending more time under tension, you would probably say that this is more critical because compression closes the crack and makes the situation less critical. Then we go from here to there. Now, which one is more critical? Well, here you can say that this point along this profile, the crack spends more time at higher tensile stresses compared to that one. Delta S is the same for all profiles, but here it spends more time under higher tensile loads, and therefore this case will probably be more critical. So that is a sort of a reasoning that one can make. And indeed, it turns out that the crack growth rate for a given delta K increases as R increases. Okay? And alternatively, if you decrease the value of R at any given delta K, you will predict a lower rate because the situation becomes less critical, and therefore this curve, the prediction of the model, will shift down. Okay, so the line will shift up with increasing R, shift down with decreasing R. Now, I have drawn it as though the slope doesn't change. Well, so what I am sort of trying to motivate here is that when I look at that equation, if R increases, the value of C should increase so that I predict higher stress, higher propagation growth rates. And if R decreases, the prediction should deliver a lower value, so C should decrease, but the slope in all cases is the same, and therefore the M value is the same for all cases, right? Now, in reality, is that the case? Not really. The slope can also change, but we are going to start with this simplistic scenario that actually is employed quite often. So the slope also changes in general, but we're going to omit it at this stage. Okay. All right. So we have a reasoning for the effect of R. That's one parameter that goes into the load profile. The other one, delta S, is already within delta K, and therefore I am able to reflect all of the characteristics of the load profile into the crack growth. I know and I understand how eventually I should incorporate different influences associated with the load profile. So now my goal is this equation works well up to the high range for a fixed R. Let me improve it so that first I can incorporate the influence of R. So my goal is here to simply modify Paris equation to incorporate the influence of R. So the Paris equation is our ideal form. We have to know that form by heart. The rest we don't need to, but the Paris equation we do, right? So now the reason we need to know it is because it gives rise to the remaining two equations that are important in crack growth. The first one is called the Walker equation, and it is valid just like the Paris equation in the intermediate region. I'm just writing intermediate starting from the low region if you like, but in any case up to the high range. Okay, so it's valid certainly very well in the intermediate region. And the Walker equation says the following. Well, the Paris equation said that the crack growth rate is proportional to delta K to some power. Depending on the value of R, this slope is not going to change. In reality it does, but we're going to omit it. But the factor increases if R increases and it decreases if R decreases. So here I'm not just going to write a constant. Instead, I'm going to write a quantity which is equal to a constant divided by 1 minus R, such that as R starts, for instance, from the value of 0 and it increases towards the ultimate value of 1, it can never be exactly 1, but as it increases towards 1, then this factor will increase and therefore I will predict higher and higher crack growth rates. That is the simple idea of the scaling, and that's what Walker has proposed. But, well, why don't we adjust it a little bit by putting here a exponent m multiplied by 1 minus gamma. I am sorry that this is a little bit cluttered. Let me attempt and erase this. See if I can do that. Yes, it has worked. So this is an exponent m, but the exponent is additionally multiplied by a quantity 1 minus gamma. So the whole exponent is m times 1 minus gamma. C0 over m 1 minus r to the power m times 1 minus gamma is the factor that we have, and everything multiplies delta k to the power m. So now, if you compare this with the Paris equation, what we're seeing here is that instead of a constant c in the Paris equation, we put a function which actually depends on r. M is the same material parameter. Gamma, on the other hand, is something that actually turns out partially load dependent. So the constants here that we need to know are C0, M, and gamma. Okay. So in some sense, the Paris equation gives us a stencil, a template, but really you wouldn't use it in reality. What you would directly use is the Walker equation, because the Walker equation is the natural generalization of the Paris equation towards the incorporation of R, which is the second most important parameter in the load profile after delta S. So this equation has everything that you need to model the crack growth rate if you can ensure that you are in the intermediate range. It works very well. All right, so that is essentially what we have presently. Okay, now, but what we cannot do is predict what happens in the high range, and therefore this is a good start, but it is not sufficient on its own. We need a further generalization to take care of this region that we cannot model. Are all of the lines that we draw here for any value of R, it's predicting a line all the way to failure. That's not going to happen. The line should curve up and give a increasingly higher crack growth rate. And that is the goal of the Foreman equation. The Foreman equation is a crack growth model that works all the way up into the high range. So it's intermediate and high range. Okay, how are we going to do that? Okay. Now, the key piece of information that we have is this. I'm going to try to somehow incorporate the fact that eventually what's happening is that we are getting closer to fracture, very close to fracture. Kmax is rapidly approaching the value of Kc, and that's why this the line in reality curves up instead of continuing on a line. So let us first write the equation and then interpret it to see how it works. Okay, so that's the form that we have. Now notice once again that this is like a C, right, of the Paris equation, except that even if R is a constant and delta S is a constant, the value of this quantity does not remain a constant. You see here, if R is constant, then C doesn't change over time. But here it does, because the value of delta K changes over time. Now, why does this work? Now, let's see why it works. So first of all, let us notice that it has constants C2 and M2. That's all it has. And notice that also I should note, the exponents m and m2, for that matter c0, c2, etc., they are not the same. They are material dependent parameters, material parameters that you find from tables that is associated with whatever fatigue scenario you have, whatever material you have. So, but apart from that, let's concentrate now on the prediction of this model. Now, as a particular case, let us imagine that r is equal to 0. When r is equal to 0, I kick this factor out of the picture. It's 1. Okay? So what remains is kc minus delta k. But something else also happens. Delta k is k max minus k min. When r is 0, it's 0 to max. So k min is 0 because s min is 0. So delta k is equal to k max. Let's just call it k because there is no min value. There is only a single value. Okay? So as K approaches Kc, okay, as the crack grows, the value of K, the maximum value, will approach Kc, okay. So in fact, let us do keep the max because the value of K changes from 0 to the max value. So if R is equal to 0, delta K is K max, and as K max approaches the value of Kc, so as this equals K max approaches the value of Kc, what happens is that this factor and let's call it C Foreman goes to infinity, right? This is 1, Kc, delta K is K max approaches Kc, this goes to 0, and this factor C Foreman blows up. In other words, the constant, in the so-called constant, the parameter in front of delta K to a constant power m2 keeps increasing if you are sufficiently close to the fracture toughness of the material. And that's going to eventually cause this curving up behavior. It will also cause a slight deviation from this line in the intermediate region, but the extent of deviation will become more and more prominent as you approach the fracture scenario. So therefore, when we look, what we've done is we've started with the Paris equation, then we've generalized it towards Walker in order to incorporate the influence of the stress ratio. And then we realized that, well, that only is valid up to the high range. So we've also incorporated the rapidly increasing crack size within the high range through the consideration of the physics, which is the fact that the stress intensity factor is approaching the fracture toughness, and that causes the rapidly increasing rate of the crack growth rate. Okay, and that's the Foreman equation. Now, having said all of this, therefore, we're going to use, in principle, these two equations. Both of them, form-wise, look similar to Paris. That's why we need to know it by heart. But eventually, when you look up in material tables, it's either this or that you're going to look for. If you're considering a scenario where the crack growth is all the way to failure, this is ideally what you would like to use, because this equation takes you all the way to failure. This one not. It takes you up to the high range, and after that it is under conservative. Nevertheless, we will always have safety factors, and it turns out that there are cases when the parameters of the Walker equation, at least in our book, is available for a certain scenario, for a certain material, whereas those for Foreman are not available. In that case, we'll work with safety factors, and we will try to make at least some prediction as to how fast the crack will grow based on the Walker equation, despite the fact that Foreman would probably be more appropriate. Now, if, however, your crack growth is not all the way to fracture, it's from some value to a rather reasonable intermediate range value, then you can use either that one or that one. So then you are safe with both. You can use whatever is available. Okay, so now we are in very good shape, but before we solve a quite nice example, let us build on these concepts a little bit further.